Okay, we are live. Hello, everyone. This is Nikolai, and this is Open Talks, Postgres TV Open Talks series. Apologies for the delay. I have connection issues, terrible internet provider in San Diego County. And today's guest is Tomas Vondra. Tomas, thank you for joining.
Hi.
So we will talk about BRIN indexes, which now has many good improvements, right? First, when they were released, I tried them and unfortunately decided to stay with B3, even though I had append-only pattern. But recent improvements look very interesting. So I'm looking forward to see the details. So since my connection is not good, let's wrap it up in terms of introduction and switch to slides.
Okay.
Oh, as usual, those who watch us online, please feel free to ask questions in chat. I will be monitoring them. Okay, thank you. Let's switch to slides. Okay, I see slides. Great.
Okay. So first of all, if you have any questions, I will try to answer them during the talk. This talk is usually like 40 minutes long. But with the questions, it obviously will be a bit longer. My name is Tomas Vondra. I do work for Enterprise DB. I'm Postgres contributor, developer, committer, and so on. And if you are, participating in the commit fests or on the mailing lists, maybe we have already met. So you can find actually those slides on my blog, which is the link is at the bottom of the page. So just blog pg-edit and the slides are there. This is essentially just the version of the talk I gave at Postgres London a couple months ago, just with changing the date and so on. So what's the agenda of this talk? I will be talking about BRIN indexes. So I will briefly explain how BRIN indexes work, what are the advantages and disadvantages. We will look at a couple Postgres 14 improvements that made it into Postgres 14. And then I will talk about some possible future improvements and maybe wild ideas that I'm presenting mostly as ideas for new patches, because this is not just a talk about like how to use BRIN indexes, but I also use it as a way to introduce new people to the Postgres community. So if you are looking for a new patch, for a patch that you might work on, some of those ideas might be a good starting point, because indexes in general are fairly well isolated in the code base and so on. So it's a good starting point. So first, let's talk about B3, which is like the traditional tree-like index in the database. Like essentially any database that you can use implements B3 indexes in some way. So the first thing you need to understand that in a B3, there's one-to-one mapping between rows and index entries, right? So whenever you insert a row, there will be a new entry in the index. The index is organized as a tree, as the name suggests. And I think it looks like mostly like this. You can imagine this like this. So you have like a root of the tree, and then anytime you get to the next level, you compare the value, and either it's larger or smaller than the key in the key, and that essentially leads you to a leaf page, and that has pointers to rows in the table, which is like row ID, essentially it's a block number and the offset on the page, right? So when you are looking for a row with a specific key, you get to the leaf, and then that gives you a pointer to a location within the data file, right? So these indexes are great for what we call point queries, right? When you are looking, for example, for a row with a specific ID in a primary key, which has a B3 index, this is what will happen, right? We will navigate through the index, through the tree. You will get the one particular row with the ID value, and that's it. But B3 indexes can also do range queries, right? You are looking for values between A and B, because tree indexes or B3s are based on ordering of the data. They can actually find the specific range of rows. They also allow ordering, uniqueness. You can do covering indexes with like a feature which is called include. They support different types of index accesses. You can do regular index scans, you can do index-only scans, you can do bitmap index scans, which is a fairly specific access through the index, and so on. So they are very, very flexible. They are very fast for most queries, but they have one big disadvantage, and that's size, right? They can get quite large because every row has a separate index entry. They can get quite big, right? So that's B3. But what are the BRIN indexes that I'm talking about in this slide deck? They actually don't have the one-to-one mapping, right? They split the data file, the table, into large chunks, like 1 megabyte by default. And then for each of those chunks, they calculate like a summary of the range, right? So for example, we have 1 megabyte, that could be like 1,000 rows, for example. And then you calculate minimum and maximum in a given column, right? On the index column. So you know that all the values within the range are between those two values. Or the summary could be something more complicated, which is used by like geometric types, for example, right? So it could be like a multi-dimensional interval for boxes, or it might be something more complicated for like IPv4 addresses and so on. And the idea is that you can then use this small summary to quickly eliminate large parts of the table, right? So for example, if you know that if you are looking for a value, then you can look at the minimum and maximum of a given range, and you know, for example, that the maximum is smaller than the value you are looking for. The value can't be in the range, right? So you skip 1 megabyte of data and continue with the next range and so on. That's the idea of BRIN indexes. The problem, of course, is that you can't actually navigate directly to a row because you don't have the one-to-one mapping. So they are not that great for point queries. They are way more expensive than B3 indexes. And they only support bitmap index scans, right? Because you just get the bitmap matching individual 1 megabyte chunks of the table. And you don't get the row granularity. This is disadvantages, but the good thing is this is actually quite cache friendly because the indexes are much smaller, and the access, if you are accessing larger parts of the table, are much more sequential than with the regular index scan. So if I need to illustrate this, so imagine that you have a table on the left of the slide, which is like one large data file, and you split it into 1 megabyte chunks, right? And for each of those chunks, you calculate the minimum and maximum for the given column, because you build an index on a column. Let's say it's a column ID, for example, and then you calculate the minimum and maximum. So you know that the first megabyte has IDs between 1 and 100. The other 1 megabyte chunk has values between 101 and 200, and so on. And you can imagine that as kind of like in 2D plane that you have as intervals, right? Essentially, on the y-axis you have the physical position in the table. On the x-axis is the range, the summary for the 1 megabyte chunk of data. And then when you are looking for a value, you essentially say, I'm looking for a value 250 for rows with this ID. And you are looking for intersection with the intervals, right? So you, for example, in this case, you know that it actually only matches the third chunk, which means that we can quickly identify the section of the table, and then the Postgres will have to scan all the rows in this chunk, right? So this is essentially the idea of BRIN indexes, and it's doing that by a bitmap index scan. So to give you a quick example, right? Imagine you have a table with a single big-int column. I will set the fill factor to 10% just to simulate like larger rows, right? Because usually you will have additional columns. So I will simulate that by setting a lower fill factor. Then I insert, I think it's like 10 million rows, but I do modulo 100,000, right? And then I create index on the table using the access method BRIN. So this will create a BRIN index. And Postgres actually gives you a way to inspect the index in multiple ways. But first, let's talk about let's look at what the index should actually show us, right? So what this query actually does, it uses the column CTID, which is a virtual column for each table with the physical location of the row, right? So it is essentially a pair with a block number and offset number. And what this query essentially does, it extracts the first part, which is the block number, and divides that by 128, which is the default size of the range in a BRIN index, which is the 1 megabyte, because pages are 8 kilobytes. So 128 pages is 1 megabyte. And then aggregates this, essentially calculates the minimum and maximum for each 1 megabyte chunk, right? So you know that the first chunk, first 1 megabyte, has values between 1 and roughly 3,000. The second megabyte has values between 3,000 and a bit over 5,000 and so on. So these are the summaries essentially that will be stored in the BRIN index. But we have calculated that manually, right? But Postgres actually gives you a way to inspect the BRIN index directly. We have an extension which is called page inspect. So what you can do, you can look at individual pages in the index and look at the summaries, right? So what the index, in this case, what the result of the page inspect actually tells you that the first block num, first range starts at block num 0, and it has exactly the same range as we have calculated before, right? Then the second index entry is for a range which starts at block 128, which is like 1 megabyte, and it has the roughly 3,000 to 5,632. Those are the values stored in the range, and so on and so on, right? If you have 1 gigabyte table, there will be roughly 1,000 index entries in the BRIN index. So we can also look at at the size of the relations in PSQL, right? So the table, as you can see, is roughly 3.5 gigabytes of data, like roughly 450,000 pages. Each of them is 8 kilobytes. And the index is, the BRIN index is roughly 160 kilobytes, which is pretty small, because if you create a B3 index, which is the second row on the slide, it's almost 65 megabytes. So it's like much larger by multiple orders of magnitude, right? So this is the main advantage of BRIN indexes, because you can have index that is much smaller, and it's like a different trade-off between the size and performance, right? So let's look at a very simple query, right? I will do a point query looking for one value, and this is the explain plan. As I mentioned before, BRIN indexes only support bitmap index scans, so that's why this is actually doing bitmap index scan and bitmap heap scan, and we are looking for essentially like one value, I think, which is, we have 100 rows for that, right? Because we have done I think 10 million rows, and we have divided that, or sorry, we did modulo 100,000, which means each value will be there 100 times in different places in the table. What this actually shows is that we are scanning roughly 5% of the whole table, right? Which is much larger, but it means we are scanning for each of those rows. We scan the whole 1 megabyte chunk. So we need to actually process much more than the 100 rows, but we do that with a much smaller index. If you did this with the B3, it would be much faster. This takes like 100 milliseconds on the laptop that I use to generate this explain plan. but obviously the problem with B3 is that it's much larger, right? And this data set fits into memory on the laptop. But once you get into much larger data sets, having a B3, it actually comes at a cost, right? Because you need to do much more I/O when accessing different parts of the index. And with with BRIN, you don't need to do that. So the BRIN indexes are great because they are smaller. And if you can accept the lower performance in some cases, that might be like a very good choice. The other problem, however, that I haven't mentioned before is that assumes and requires correlation for efficient elimination of ranges, right? This works great, for example, if you have data that are like increasing over time, like timestamps or sequential IDs or stuff like that. But obviously, if you have random data, like for example, you are not using sequences to generate IDs, but you are using like UIDs or IP addresses or some other type of data which is not increasing over time, that's going to be a problem. And I will show you why on the next slide. The other problem is that even though the initial data may be nicely correlated, that will degrade over time if you do like updates or deletes or whatever, right? Because Postgres actually doesn't use this correlation when it decides where to place the new data. It does that simply based on information about free space on each page, right? So for example, you may delete some old data with old timestamps. Vacuum will clean up the space, and then Postgres will happily insert new rows into the place in the table with new timestamps, completely breaking the correlation. So
I have a question, but I'm not sure if you can hear me well.
Yeah, I can hear you.
Great. So we have a question in chat. With high volume DML, how can we maintain the BRIN index? And I guess we will discuss it right now, right? If we have a lot of updates and deletes, is there any chance to use BRIN efficiently, right?
So I don't see why that would be a problem, because you need to maintain the B3, right? If you need an index, you need to maintain the index in any case, right? I think it's actually even cheaper with BRIN indexes than with B3, for example, right? Because you are only maintaining a much smaller index. So I'm not sure exactly why would like
right. It's interesting, like we discussed maybe yesterday even, for example, if we have unused index, we might think that maintenance of it is like 0 because nobody is using it, but every delete needs to touch the index, and touching B3 is much more lighter, right? Because less blocks need to be loaded to memory, right? I mean, like it's smaller, so overhead is smaller.
Yeah, you mean BRIN? For BRIN, the overhead is probably smaller. Yes.
Right. But here is my additional question. Sometimes, like if they think like, okay, index is very light, updates overhead during updates is very small, we have a tendency to create it, like to use more BRIN, several BRINs sometimes. But do you think it can be sometimes dangerous because we can lose hot updates faster, because more updates will become non-hot, non-heap only tuple?
Yes. I think the assumption that cheaper indexes allow you to create more of them, I think it's a fallacy. I mean, like, I think it's bad engineering practice, essentially, to create indexes without considering the costs. I mean, like, it definitely is not the case that if you create additional indexes, but don't use them in queries, which I'm not sure how exactly you can be sure of, I think it definitely has a cost to maintain the indexes, right? Both directly, because the database simply needs to, update the index, but also indirectly because it blocks some optimizations, right? I mean,
simple example. For example, we have a table with ID column, which is like integer 8.
Yes.
And created at and modified at 2 timestamps. And we modified at column quite rarely. And before our decision, we didn't want to create a regular B3 index, but then we started to think, okay, we have BRIN indexes, they are very light, let's create BRIN index on modified at column. And immediately updates which were probably hot before our decision, because this column was not indexed, they become non-hot, so they become much slower, and all indexes needed to be touched during such updates. So updates become much heavier, right? So this is a very practical example, I think.
Well, yes, I mean, I think it's definitely the case that BRIN is cheaper to maintain than B3, but it's not like an excuse to create unnecessary indexes. BRIN is just like a different trade-off between, costs and performance. So, but the cost is still non-zero, right? So I'm not sure how else to answer the question.
Well, the question is unclear because it's an unclear topic, because I see that most people usually don't take into account the hot updates and how they can be easily lost if you try to optimize the index set.
Right.
This is a problem. Like, we don't have good tools for good analysis here, usually.
Right. So I think BRIN indexes are definitely, they may work as a replacement for B3 in some cases, in which case you are already like blocking the hot updates anyway. But if hot update is an important feature for you, for your workload, then obviously any type of index will be an issue. But then the question, however, is like, if you don't create the index, can you actually evaluate the queries that you need to evaluate, right? Like, because if you don't have the index, maybe the query starts taking, instead of like 1 second, it will take a whole day, right? And at which point it's kind of unusable for the user. So I think it's definitely like a complex thing to answer. I mean, I don't have a simple answer to that.
Okay, thanks.
Yeah. So I've been talking about the importance of correlation for BRIN indexes and how they are, like, at least for the min-max indexes, how they rely on that. So let me give you a quick example. Like, imagine the same query, same data set that we had before, but we now update 1% of the table to have value 0, and 1% of the table to have value, like, essentially the maximum, which is like 99,999. And we just update 1% of rows for each, right? And then if you repeat the same query as before, like searching for value 4,000, which is like somewhere in the middle, instead of scanning 5% of the table, which is like a couple blocks, couple ranges, we suddenly start scanning 100% of the table, right? Because we have updated just 1% of the rows, but it made the ranges so wide that for each 1 megabyte chunk, we essentially had both the 0 and the maximum value in there. So each 1 megabyte chunk matches the condition. We are unable to skip some of the ranges. And in this particular case, it ended up running for like half a minute, right? And that's annoying because a simple sequential scan would be just 5 seconds, right? So it's actually an example of poorly planned query because we don't have a very good estimate of what fraction of the table will we scan, right? So that's a problem with the optimizer, or like a principal problem of query planning. And if you look again at the, at page inspect at the index, you will see that the ranges are essentially each of the 1 megabyte chunks has minimum 0 and maximum 99,000 and so on. So the blocks will match all queries, essentially. We will always scan 100% of the table. And this is a kind of extreme example, but essentially what's happening is this, right? Yeah, there is a mistake on the slide. The min-max should be 0 and 99,000 in all the cases, which means all the ranges in the table have this summary. And then when searching for a value like 250, all the ranges actually match, right? They intersect with the summaries. So this is a principal problem for BRIN, right? Because we then need to scan the whole table, and we need to check all the rows only to eliminate like most of them. And this is actually the first improvement in Postgres 14, which we call minmax-multi. The idea is that instead of keeping just a single min-max summary for each 1 megabyte chunk of the table, we actually keep multiple ones, right? Which allows us, if you have outliers like the values 0 and 99,000, we can keep them as separate points, right? And we don't kind of degrade the summary into one extremely long interval. We keep like multiple small intervals, which means that we can still, eliminate most of the ranges, right? So for example, if I create the min-max-multi with if I create the index with the new opclass, which is how we call variants of indexes, you can see that it actually performs even better than before, right? I mean, like instead of scanning like 5% of the table, we scan only like 2.5%, and we are mostly back to the original timing. Yeah. So this helps with the data that is mostly correlated, but there are some outliers, right? And it also helps with data that would degrade due to Postgres, moving some of the rows after update and so on. It degrades much more slowly. Obviously, there are like similar opclasses for other data types, not just for integer, not just for big int. And I've also mentioned that the BRIN indexes that we used to have before don't really work for data that is not correlated at all, right? I mean, like if you are, for example, inserting data about IPv4 addresses or UIDs, those are mostly random, right? I mean, like especially the older UID types, for example, are perfectly random. But there is no correlation because you, for example, if you have a logging table which you are inserting data about, visits to your website or wherever, including IPv4, those will be completely random data. That the IPv4 addresses will not be in any particular order or anything like that, right? So what we actually can do in Postgres 14 is you can create a specific Bloom index, BRIN index, which is based on a Bloom filter. So instead of the minimum and maximum for each 1 megabyte chunk, we keep like a small Bloom filter tracking which values were observed in the 1 megabyte chunk of rows. And because it's not based on ordering of data, it only supports equality searches. We can't do any range queries, searching, for example, for UIDs between 2 values or something like that. But the good thing is, obviously, people generally don't need to do those queries. So if I create the index specifying the operator class, similarly to before, except that I'm generating like UIDs, right? Then this is actually pretty good. We will scan about 13,000 rows, 13,000 blocks, 8 kilobyte blocks in this case, of course, and the query will run in less than a second. So it's like still much faster than sequential scan, but it's obviously slower than a B-tree. I mentioned that the Bloom filter, the Bloom index is based on a Bloom filter, of course, which means there are some tunables, right? So you need to, if you can tune the index, but you need to provide additional information about so how many distinct values will we see in 1 megabyte chunk, and what's the false positive rate that we want to get. If you created the BRIN index as before, using this query, without any parameters, it would be 34 megabytes. So not that much smaller than the B-tree, which is 70 megabytes. But if you tune it a bit, you get it much smaller, right? You get it only 8 megabytes or something, and it will still give you pretty good performance. I don't have an example here, but the idea is that you are exchanging, false positives, which means a fraction of the table that you will need to scan, and you are exchanging that for the size of the index. The reason why the tuning actually works is that we only have, very limited information about the new that we can use for the creating of the new index, right? You are, for example, creating the index on an empty table, so you don't even know how many distinct values will be in the column, and we don't have a very good way to, learn this from the data when creating the index. So we use some crude estimates that are, in this case, turned out to be to be like too strict. So the index was created too large. So those were the two new improvements in Postgres 14. It's actually fairly simple to implement custom opclasses for BRIN. So if you have any other data structure that you think might be useful for, like the summaries, because the BRIN indexes are building summaries for small parts of the table. And if you have some other ideas, you can try implementing that. But I also have some ideas for improvements in BRIN indexes that might be interesting for future Postgres releases. So the first one is insert retry. Because the summaries of the BRIN index may be fairly large, even for the original BRIN indexes, not for the new ones. Index entries are kind of limited to, they don't use toast. We don't use toasting for indexes, just compression. So if you have a large value and you create an index on that column, maybe the index can't even be created, right? Because, for example, that's also true for B2 indexes, right? If you have a long textual value and you try to create a B2 index on the column, that will fail because we only allow we need to fit all the values on the page, right? And for BRIN, that actually is even more annoying because it's both kind of unpredictable, and we also need to store multiple values for in the index tuple, right? Because, for example, if you have the original BRIN indexes, we need to store minimum and maximum, right? And it can happen that each of those values is like reasonably small, that you could index the column using B-tree, but if you combine them and you need to store both of them in the same BRIN entry, essentially, suddenly both of them are larger than the 8 kilobyte page, right? So they don't fit, and the insert will fail. But it's unpredictable because
sorry, and this can happen later. Like we create index, it looks fine for some time, but later we try to insert very large value, and it happens to be on the edge, right? I mean,
right. So that's what I meant by unpredictable, because for B-tree, it can happen, of course, even for B-tree, right? If you try to insert much larger value, that will fail. But for BRIN, it's actually even more unpredictable, because it also depends on where exactly you wrote the new row. So, for example, it gets inserted into a page range where the summary is already quite large, because the minimum value is, for example, quite large, and you need to suddenly add a fairly large maximum value, right? So suddenly it fails, but then you try the insert again, and it succeeds because it gets inserted into a different page, into a different range. And in this case, the minimum was like much smaller or something. So it depends on which other rows are in the range. And that's why I've been thinking about like doing the retries automatically, or so that the user actually doesn't need to deal with this, right? Because the application needs to retry the insert anyway, and it's super confusing, right? Especially because it's not about the table, but it's about the indexes.
Yeah, this is good advice. Application should be able to should be ready to retry writes anyway. Unfortunately, not everyone follows this rule.
Yeah, right. And it's also the case that sometimes the indexes are created later, right, after the application was already developed. And also, the question is like, will the retry actually succeed? I mean, like, maybe the value is really so large that we even retrying will not fix it, right? So that's really hard for the application to reason about, because also this depends on compression, right? We do compress the data, we just don't toast it. So it's very hard for the application to know if the insert or if the retry is actually worth it, right? We don't know that.
For BRIN case, isn't like, would it be possible to maybe to store not the whole value but only the part of it, to like just to determine the edge? So just some, I don't know, like if it's a character, right, just cut it, right? Why not?
Yeah, like an abbreviation, right, or something like that. I mean, like that would be interesting, and we don't have those summaries, especially not for like text, right? I know that we are using abbreviations when building an index, but I don't think when building B3 indexes. But I know that there are some problems with actually deriving the abbreviations and keeping them stable, right? If you are interested in that, I mean, this would be an interesting BRIN op class for text, for example. I think that would be interesting. But I'm pretty sure there are problems with like collations and so on, which is why we only use that to build the index, but we don't actually use them in B3 to store the data, right? Okay, so there was like the retry was the first idea. The other idea that I think BRIN would be really interesting for is actually using them to route the new inserts, right? So for example, if you are inserting data into a log table, and one of the columns is a timestamp, and it has a BRIN index on it, maybe if you are inserting, data, make sure that we don't insert them into pages that are in old ranges, right? So kind of to minimize the size of the summary. Like don't insert them into ranges that would extend the the min-max range too much, or something like that. I haven't really thought about like how to do this with like multiple indexes, for example, but I think it shouldn't be that difficult with one particular index, for example. Essentially, what the code currently does is looking at the free space which we keep in like a cache, and we could also look at like multiple candidates, for example, from the free space map, and also look at indexes at the BRIN index and see how that matches with the existing ranges. It's not going to be for free, but I think it would be interesting. And then we have some other ideas, like other types of summaries, right? So you have already mentioned the summary that isn't storing the whole string, for example, but only like a prefix, right? So I think that would be one option for at least research, right? The important thing here is that false positives are okay because the index is only used in the first phase of the BRIN index scan, and then we recheck actually all the rows in the matching range, and it's a size efficiency trade-off, right? So, for example, in this case, you might use shorter prefixes, but that would be size efficiency trade-off because shorter prefixes probably mean that we would match additional, ranges than necessary, and so on. The other idea is actually using BRIN, particularly the cases actually relying on sorting, like min-max or multi-min-max and so on, and use that for sorting the data. Right? I mean, I have mentioned that we can use B2 indexes to do order by in a query, for example, or we could even do like group by based on index, of course. But we don't do that for BRIN. But I think BRIN might be quite efficient for like top-end sorts, right? Because you are able to kind of combine the pages and incrementally sort more and more data until you produce the top-end results. And this was actually already discussed at the PGCon this year at the unconference. So it's not a completely crazy idea. And the last thing I've been thinking about is like if we could use BRIN to speed up count in some cases, right? I mean, like we would need to improve the summaries so that the summary actually keeps information about how many rows are in the range. And we would need to look only at ranges that we know are all visible. I mean, like there are no dead rows, there are no rows that might be invisible to some of the still running transactions and so on. But I think it should work. The problem, of course, with this optimization is that it only works for queries without any where conditions, right? So if you do select count from table, that might help. But as soon as you add a where condition, that will not work for BRIN indexes or evaluating the count from the BRIN index, because we also need to look at some other columns in the table, and we don't know how to do that just on the BRIN summary. So that was all. That was all the talk. So are there any other questions?
Yes, there are. First of all, we actually had an interesting discussion about hot updates, and with help from chat, I found your commits last November. You committed optimization to allow heap only tuple check to ignore BRIN indexes, but it was reverted in June.
Yes.
Also by you. This is interesting. Again, in chat, people say that there are chances that it will come back. There is some prototype to fix the issues found, right?
So I think there was some discussion. I don't remember the details, but I know the implementation was buggy in some cases, and so. But I think that the discussion was that, or conclusion was that, we could do at least some of that, some of the optimization. Yes. I mean, like, we can't ignore the BRIN index entirely, unfortunately.
Makes sense. And there is an interesting question as well. Thinking on the route inserts and updates, is it possible to BRIN index help to tables that are clustered to be maintained automatically without the need to recluster periodically? So it's not possible in your opinion.
So that was actually what one of the future optimizations of the IDRs was about, right? That was the use BRIN indexes for routing of rows into the proper location. So I think it should be possible, but it's not implemented there, right? I mean, like,
right. We talk about future, of course. Yes, it's not right now.
So,
but
I think it should be possible. I think like a prototype wouldn't be too difficult to implement. I'm proposing these things because I'm willing to help the people to implement those things. Right.
Yeah, this is interesting. So it means that we don't need, like, if we see that we can benefit a lot from clustering, usually we run something like PostgreSQL with clustering option to do it online, because cluster command is offline command. But in this case, we would not need it at all, because the state is almost in perfect. I mean, we have almost perfect state constantly, right? This is cool feature. I would like to have it. So it means that it would mean that we want to have BRIN index not for just to speed up some queries, but to maintain physical.
Yes.
Yes, to maintain physical distribution of rows as we want. Interesting, right. Very interesting. This is cool. I even didn't think about it, like something very, very new. Okay, thank you so much. I learned a lot. It was interesting. I'm going definitely to try optimized BRIN in Postgres 14. Looking forward for future optimization. This is great. Thank you so much. Again, apologies for issues with internet. I hope someday I will resolve them. California is quite wild west, you know. We have problems with providers. Again, thank you so much. Our audience, thank you for great discussion questions. If much more people will watch this recorded, so encourage everyone to ask questions in comments. I will be monitoring questions and deliver them to Tomas to bring answers in asynchronous mode. Thank you. Good luck with future development of such things. I think it's very interesting how we know indexes in Postgres are already very powerful, but new horizons appear constantly. This is great. Thank you.
Yeah. Thank you for having me.
Thank you. Bye-bye.
Bye.